Hello there. My name is John Saunders. I work for the Health and Safety Executive in their Science Division. Within my team, there's a range of us that work on noise and vibration. We cover respiratory protection equipment, and we cover extraction, local exhaust ventilation. That's my topic, and that's what I want to talk to you today. In particular, looking at the use of LEV for extracting welding fumes. So I'll just share my screen now with you. This presentation will cover quite a few aspects. I'm going to try and run through the whole remit of right from the design right through to managing a system. The first part of the presentation, though, is going to be more about the review of the type of designs that are used to control welding fumes. And then the remainder four topics are more along the lines of actually managing and procuring an LEV system. Okay. So looking at LEV designs, there's quite a few solutions, and really you need to pick the one that suits your type of welding, and that will depend upon the size of the piece that you weld in, how frequently you weld, etc., whether it's outside, inside. Broadly, these are probably the four most common solutions. You have the top left, the extractor booth. To the right of that, you'll see the downdraft table, where the extraction is through the table surface. Probably more common at the bottom is and that's bottom left, the capturing hood. And bottom right, used more and more, I'd say nowadays, is the on-torch extraction. Three of these are basically very similar in their design process. They are all capturing hoods. These rely on the process actually is outside of the hood, whereas if you look at the first one, the extracted booth, the process is inside, and the extracted booth is probably the preferred option if you can, if it works for you. And I'm going to start with that one now, and then we'll have a look at the different types of capturing hoods, and I'm going to focus on capturing hood bottom left and the on-torch extraction after that. So let's have a look at an extracted booth. These come in all shapes and sizes. And as I say, the difference between a booth, an extracted booth, and a capturing hood is that the process is inside of the hood. And the beauty there is it's not, well, I won't say it's immune to drafts, but it's much more robust against any cross drafts. And because it's inside the booth itself, the booth doesn't have to capture. All it's got to do is contain that fume and draw it away from the worker's breathing zone. That's the role of the hood. There's two examples on the screen there. The bottom left isn't the best, and I can tell you why straight away, you may have spotted it, is the worker's got his head inside the booth. So design of the booth is important. I'll come on to that a little bit in a little while. But the top one, you can see that there is quite an open booth, and that could easily also have downdraft capabilities. It might be extracting through the bench and extracting through the rear, but usually they are extracted at the rear of the booth, and it removes the fume away from the worker's breathing zone. And these are usually the most effective. They are limited in their use because of the size of the booth and what size workpiece you can really use with it successfully. So you'll see the booth at the top. It's the two doors either side that are basically kind of hinged, and the one on the bottom's got the transparent strips. So it pays to spend a little bit of time and think about the type of booth that suits your operation. You spent a lot of money on an LEV system, the filter, the fan unit. What you don't want to do is just put a box on the end of it. So you have to think about the ergonomics, lighting, how you're going to use it, access, etc. So that's basically your extractor booth, and I say that's usually the most effective solution if your workpiece can fit in. Capturing hoods, I'd say, are probably the most common, and I think if you mention to anybody that works with LEV and you say, what does LEV look like? A lot of people always seem to come back with the movable arm, which is the bottom right-hand corner, and also the bottom center one there. And that's the one that people think of LEV. And with capturing hoods, as I say, the process is actually outside of the hood, and it's what you've got to do is move the hood to ensure that you capture the fume. And these capturing hoods come in all sorts of different shapes and sizes. So the top three are relatively small, and that ruler you can see there is 30 centimeters long. So it gives you a feel for how small they are. Doesn't matter how big the booth is, the hood is, They all work on the same principle. The process is outside, and the hood effectively has to generate an airflow in front of it and pull in the fume. They can be effective. They often fail, and it's because of incorrect use. It does rely on the worker to understand how limited that capture zone in front of the hood is, and therefore the need to keep repositioning. So training is required. This image is just gives you a feel for the limitations of capturing hoods. So the welding fume will be outside of the hood. There's the opening here on the right, and these curved surfaces, these are basically kind of contour lines of the velocity, and these are falling away from as they move away from the hood. So let's just say the hood had a phase velocity of 10 meters per second. If you're roughly 1 diameter away, you can see down to 10%. So rule of thumb, 1 diameter away from the hood, you're down to 10%. So it drops off incredibly quickly. And that's because it induces an airflow from all directions. So that is really what you'll typically is the usable volume in front of a capturing hood. It's 1, maybe 2 diameters from the hood. Beyond that, you've got a very low induced flow into the hood, and you'll probably find it fails unless the fume is rising naturally buoyantly into the hood. So just to go over this one more time, let's have a quick look. This is a setup with this is a worker, and this is typical. It's been set up for filming, but this is based on real life. So this worker's welding on this kind of table affair, and they can see where the extraction hood, and this is being positioned by the worker because it's out of the way. The reality is, as you can see, the fume rises. Some of it goes in. The majority is just passes through the worker's breathing zone, so it's subtle exposure there. And I'd say, what, 90–95% isn't even going close to the hood. And this is typical. The worker moves position, and now it's in the right position. You can see the fume is now entering the hood. It's within that capture zone, and that's probably just over 1 diameter away. But because the worker moves on to the next part, you'll find that as they move, typically the hood isn't moved with the process. And this is why you'll often see the hoods in the wrong place for a lot of the time. And of course, that fume then escapes into the background and pervades the whole workplace. Okay, so that's the Achilles heel of capturing hoods. You've really got to be on top of training, and you've got to be able to move it continually. So the hood has to be movable over the entire workpiece. Another form of extraction, which is becoming more popular now, and the designs have improved. It's only for MIG and MAG, but it's a form of capture hood. And you can see on the right-hand side there that the fume is generated at the weld pool, and the extraction openings are actually integrated into the torch itself. In this case, they're quite far away, but this is just an illustration. So you have the shielding gas coming past the contact tube, bathing the weld pool. Fume comes off, and then it's captured within the torch itself. So it's integrated into the torch. The beauty about this type of design is that you do not have to move the extraction. It's built in. So it's always in the right place. It might not be 100%, but it's always in the right place. The flow rate is relatively low for these type of devices, probably 50 or 60. If you think of the numbers, 50, 60 compared to 1200 for your movable hood. So much, much lower flow rates, and they can be effective. The advantage with these hoods is, as I said earlier, basically your extraction moves with the torch, so there's no need to reposition. Also, if the torch can reach the weld position, then so does the extraction. So it's not limited by the size of the workpiece. So it becomes very flexible. Doesn't matter if the workpiece changes from day to day, the torch can reach it, the extraction does. Potential disadvantages, they are slightly larger. It depends on the design, and they are getting better and better. If a few years ago they were not as good as they are now, really down to design and also down to materials used. So they were heavy and cumbersome, but now they are much, much better. The other reported disadvantage of them is weld porosity. Now, we did a study some years ago with the Welding Institute, and we actually did a number of welds. We measured the emission rate, we measured the capture efficiency, and we also looked at the weld quality visually for surface porosity, but we also did x-rays of the welds to look for subsurface porosity. And all of the welds that we did on our tests, and we did fillet welding, we did downhand welding in position, all of the welds that we looked at had no porosity. So whilst I accept some people have commented you can get porosity, I think it's in certain situations. It may be in a very tight enclosed internal corner maybe, but for most situations I think you'll find that the weld quality will be just fine. The other disadvantage is because they are high pressure, you won't be able to use your existing extraction system. So if you've got a mobile system that runs a capturing hood, then you'll need a new system because it runs at a low flow rate and a high pressure. So this is just an example of showing you of the effectiveness. So on the left there, this will be a video without control, and on the right it'll be with control. Now, if you just before I move on, if you look at that hose, you'll notice it is a little bit wider than a normal hose, and that's because it's not just carrying the cable and the water cooling if it's got it on the torch. It's also you need space in there to get the air through, and that's why it's a little bit more cumbersome, but not a lot. You'll also notice they've got a sleeve over the plastic ribbed tubing, and that makes it easy to slide over the workpiece piece. And also it protects the plastic from damage from spatter. So that's a neat idea to think about. So this is typically you'll see the weld fume there. So you can see the weld fume rising. It disappears into the room because it's not lit, but there's a lot of fume rising. This is the on-torch extraction. This is the same welder, same weld, just with the extraction on. And as you can see, very good control. And the welder reported no problems with this at all. So it can work, it does work, and there's some evidence. I'm going to come to checking LEV systems and how you check flow rates, but I'm going to mention it now for on torch, just while we're on the subject. Normally you check a hood either at the face of the hood opening, or you check it in the ducting to check flow rates and phase velocity. It's not simple with on torch because they operate on this very kind of high under pressure. Then any leaks in any part of the system are exaggerated, and you get a potentially high leakage. There was 8 systems were checked, and all of them leaked. So in other words, you've got less going into the torch at the front, and kind of leakage throughout the whole system. So if you measured it at one end, you'd end up with a higher value than at the front end. So the best way to check this type of torch is basically just a flow meter that slides over the front of the gun. Often it's usually a ball or a float that raises and gives you a green area or an amber area. So it's very good as a quick check, once a day, once a week, just to make sure that you're getting the right flow rate at the torch. And mainly it's because of things like the swivel joints and hose connections. You've got the power cable coming through the hose. You've got potential water cooling, and that's where the leaks occur. And they can get larger, I guess, with time. So that's why you check it at the front of the torch. We'll come back to checking LEV systems towards the end. Now, thinking about filter systems, once you've managed to capture your fume and it's in your LEV system, you want to ideally filter it and discharge to a safe place outside. That's the ideal situation, and most central systems will do that. However, we do recognize that many systems will recirculate back into the workplace. And the reason for that is often because maybe you don't own the building, so you're not allowed to punch holes through the fabric of the building. You may not have got planning permission for stacks, etc. So there are systems available which will recirculate the air back into the workplace once the air is thoroughly cleaned. You've got to, it's advisable to make sure you maintain these systems much more robustly, because if the filter fails, then you're returning fume back to the workplace. So it kind of fails to danger. If you're looking for different systems, many of them, and I'll put a note at the bottom there, have a final filter of a HEPA filter, high efficiency particle air filter. They're very high efficiency, it's almost like an absolute filter. Alternatively, you have systems marked to the standard you can see there, 21904. And this is slightly different because this is, you'll see these systems marked with W3. And that means it's got a capture efficiency greater than 99%. But that's not been tested with a surrogate particle, it's been tested with Welding fume. So that's a process where you generate the fume in front of the hood and you measure what's captured. So it takes into account the whole system, including the filter housing, how it's fabricated together, any leakages, all of it is taken into account. So it's quite a good standard in that effect, in that it gives you a confidence that it will work against Welding fume. So think about taking extra precautions, particularly, as I say, if you are discharging that air back into the workplace. Final filter, you might want to consider a HEPA filter. Many systems come with HEPA filters now that are designed to return air to the workplace, and potentially monitoring filter efficiency. That's not as easy, but you can do it with particle filters. Alternatively, you can look for blockage on your filter by taking a pressure drop across it. We'll come to that later as well. You will have seen, and many of you may come across or have these extraction units that are mobile. The mobile ones will have filters in, they will return the air back into the workplace. They're often fitted by a manufacturer will fit an alarm to them. It's usually either a low flow alarm or it's a pressure drop across your filter telling you that your filter needs changing or cleaning. Some of them you can clean them on the actual system themselves. They are useful because they are flexible and easily moved around if you've got large workpieces or the workpiece changes from day to day. But you need to remember with any system that recirculates that having good LEV is not an excuse for having poor general ventilation. It does return the gases back to the workplace. The filters only filter out the particulate matter and not the gases. So you're relying on the filter performance there for the particles. If you've got lots of these, the cost can increase because you'll have individual filters and fans, etc. So lots of companies look at centralized units, and this is where essentially you have a fan and filter unit, usually outside, discharging into atmosphere and connected to a number of welding stations. So that's kind of a more of a planned system, and you've just got one system with multiple hoods. I just want to touch on standalone air cleaners. You see quite a few of these cropping up. These basically, from the outset, these are not LEV, and they're not a replacement for LEV, but these tend to draw air in at a high level, passes it through a filter, and then discharges it usually at a lower level. So they're great as a supplement to LEV to improve maybe the general air quality for any fugitive emissions of other processes, maybe, and the odd part of welding fume that isn't captured. But they are not an excuse for not having LEV. They are a supplement. So I just thought I'd mention those. So that's a kind of a bit of a canter through LEV design. And as I say, the hoods and the booths are the kind of the best choice if you can go for that. And then you're down to the on torch and then your capture hoods, and it does depend, except it does depend on the size of your workpiece. So for the rest of the presentation, I'd like to think about the procurement route, about how we get LEV that works not just on installation, but continually works week after week, month after month, year after year. This is an example of good practice, and I'd say that this is any LEV. It doesn't need to, it's not just welding fume, but this is where the employer recognizes they've got a problem, they've done the risk assessment, they've identified sources, maybe even some missed sources, so they know where they are with that. They then approach it with the hierarchy of control, where you'd start with elimination, substitution, and you work your way down. And the blue oval there is where LEV fits in under the engineering controls. Except for welding, it's difficult to eliminate unless you can join your pieces of metal together in different ways. You may be able to emit less though by just altering your welding parameters. So often there's a graph in textbooks where it shows you the welding fume emission drops before going up, and if you can keep it at the bottom of that curve, you can actually reduce your emission. So that's the kind of the hierarchy of control you'd normally do. And consider process change, but as I say, with welding it's a little bit more tricky, I accept that. The next step is you decide you want the LEV, you now need a specification. I'm going to come into this in more detail, but basically it's a specification of what you require. It's then installed, commissioned, and tested against the specification and then shown to control. It's then checked and maintained regularly. And then the annual thorough examination and test that's a statutory requirement is carried out. And then it's a bit of rinse and repeat. You're making sure you're checking, maintaining it, and annually testing it. Unfortunately, this is often doesn't happen. And what you find is that sometimes the employer perhaps is told that they've got a problem, or they grudgingly accept that they've got a problem, and it becomes a bit of a grudge purchase. And what tends to happen is the process control change, or the hierarchy of control, is ignored, the specification is missed out, and then you go straight to basically buying a system that you think works. It's installed, it's not usually commissioned, checks are, because it's been installed and not commissioned, you don't really know what checks need carrying out. And then you're at the end of this cycle and you're relying on the thorough examination test to pick up problems, and that's not the best way to go. It feels like you're perhaps saving money by jumping straight to purchase, but you're not. It's false economy. So let's have a look at the steps. So we'll miss out the sources. We know what the source is. We've got a welding source. We can't change the process, but we do need LEV. And these steps, it depends on the resources and the complexity of the LEV system. And I accept that small companies might need a little bit of help at some of these stages, particularly maybe on the process change and maybe even on the specification. So the specification, it's worth looking at. There's INDG 408. It's a free downloadable guide. When this was drafted, there was no other guide available to buy LEV. So it's as far as we know, it's probably still the only one. So it's worth having a look at that. And then it's a case of writing a specification. It doesn't need to be a large document, but it's something that you're writing down that you need. It'll be how many workers you've got in the workplace, how often you're welding, what are you welding, what materials are you welding, how many welding stations do you need, etc. It's this type of document. You want to specify the use of HSG 258, which is the LEV guidance, which is a link at the back of this presentation towards the end, and the principles that are specified in that. And you also think it's things like, you require test points. You need to have test points on the system so that you can check that the system is performing as expected. Inspection hatchways on long runs. You need inspection hatchways in the filter, things like this that you ask, and they need to be accessible. It's no point putting an inspection hatch 5 meters up in the air. You also need to think about a user manual. You need to ask for a user manual, particularly if it's a complex system. Maybe it's a bespoke system, a centralized system throughout your workplace. You want the user manual, you want some way of a logbook to tell you, so you can allow you to record what maintenance you're doing. You need to know what maintenance to do, and you need some training. And it's worth, when you're having a system put in, to specify that you want the workers and possibly the management will look after it to be some training for them to bring them up to speed. You also want airflow indicators to be fitted, and I mentioned those earlier on the kind of the mobile systems that often have alarms on. It's that kind of thing that you'll have an airflow indicator that allows you to know it's running properly. So, for example, for a welding booth, you would have probably a pressure gauge with a green and 2 red areas, and it's kind of basically the needle wants to be in the green. If it's not in the green, it doesn't tell you what's gone wrong, but it does tell you something's wrong. It could be a blockage in the system, it could be a split in a hose, etc. So the operator knows there's something wrong with the hood, and then you can investigate. So that's your specification. So it's installed now. So these 4 steps. You could argue that the first step, installation, is not really commissioned, but let's just accept it is. So if we install in it and we verify it's installed as it was designed. The second step is you show it meets the specified technical performance. So this will be what basically is you've agreed to have installed, and it's what's been designed. Now, often the third and the fourth step get missed now. It's installed, it's moving the right airflow, and you're good to go. The reality is, yes, the LEV system is designed to move a specified amount of air, but really it's not moving just air, it's controlling welding fume. So it's control effectiveness. It needs to be demonstrated, it meets the benchmark. Is it moving the right amount of air, but is it also controlling exposure? So that's down to the checking the design. And the only way you do that is to make sure it actually works with real welding fume. And the fourth step is the commissioning report. The commissioning report is key because this lays down the benchmark of what was installed, what the variable parameters are, whether it's pressure in the system, velocities at certain points, how you use it, the position it's used, etc. And that is all captured in that commissioning report. And that's your baseline for future performance testing. So you've got your system installed, you've got your commissioning report, and you've got your kind of maintenance manual and your logbook. So now it's a case of making sure that you carry out your maintenance and make sure it continues to perform. And on the right is typically what happens. We think of LEV as being kind of, big metal parts, hoods, kind of quite a robust system, but they can be quite delicate and they can go out of balance quite easily. And so it's the preventative maintenance to bring it back up to that acceptable level. So it's kind of a physical check on the system. Is the filter blocked? Are your airflow indicators operating as expected? So it's just doing the maintenance that's in the logbook. Anything it gets damaged, and typically the flexible hosings, if you're using those are the ones that tend to split or are crushed, make repairs and keep checks and keep records. So then you move to the thorough examination test. So this is essentially every 14 months, but it's a yearly test essentially. And this is a statutory requirement, and you need to have this done annually. And this comes, if you think about this test, this is coming right at the end of the chain. This is after it's been installed and been running for a year. And it needs to be carried out by a competent person. It could be an internal person within the company, but usually it's an external person that will come into your company and check and give you a kind of a thorough examination test of your system. To do that, the examiner, he or she who comes into your workplace, may not have seen your system before. They're starting with a blank canvas. So you need to provide them with the user manual to tell them how you use it. They'll need the commissioning report so they can see what values they're measuring the performance against. And also, have you changed it in any way? Have you added an extra hood? Have you changed any part of the system, a design of a capturing hood to an enclosing hood, like a booth? So you need to keep the information and present it to the examiner. And the actual examination, it can be divided into 3 steps. You've got your visual examination of the system. And this is making sure it's actually in working order. And this is the first thing you do. You don't want to go out and start measuring pressures and velocities. It's an internal and external examination of the system. And often the examination and test can fail at this point if clearly things aren't correct. Hoods aren't connected, hoses are badly split, so you're just not getting the airflow at the hood. Once the examiner's carried out that thorough examination test, is happy that the filter integrity is okay, etc., then you'd move to the actual measuring and looking at technical performance. So this would be measuring the airflow, the pressure at certain points in the system, and comparing that to the commissioning data. And if there's a problem there, maybe the flows are low, then you can see where that's going to lead to in the report, where it'll identify issues you need to deal with. The third step is then making sure that, yes, it's moving the right amount of air, but is it still controlling exposure? And that often you might see examinations being carried out with smoke, but with welding, the easiest way is to watch the welding, because you're also watching the process and you're watching how the workers use the system. So you might find out that the examiner comes in, it's moving the right amount of air, but the workers aren't trained and they can't, the hoods aren't in the right position, etc. And that would be included in the report. So when you as owner or employer get a report, you then should have a list of actions, hopefully a small list, and you treat this this kind of thorough examination test report as an audit of your internal management system. If you end up with a yearly action list that's as long as your arm, it's really saying that you're not maintaining and looking after your system throughout the year. So once you've got that report, you want to act on them controls and maybe review your schedule for your tests, maintenance tests, and what tasks you carry out. And importantly, to demonstrate you're having this thorough examination test carried out, which is a statutory requirement, you need to keep it for a minimum of 5 years. So what can go wrong with, there's quite a few things that can go wrong with thorough examination tests, and over the years I think many inspectors have seen most of them, but this is typically what often happens is the examiner's not got enough information when they come to see the LEV system and test it. So there's a lack of commissioning data or no commissioning data. The previous text reports aren't available, so you can't see whether there's been a drop-off in performance over time. And there's no user manual, and that's not really it's not good for you. You're not getting the most out of the service you're paying for, and it's not good for the inspector because they are having to almost kind of try and commission the system on the fly. So it results in usually a poor thorough examination test. Sometimes it's the examination itself. It's not thorough, and you often or used to see kind of single sheets of a thorough examination test where it just says the airflow's fine, and literally it doesn't say any more than that. So it's got to be a thorough test of the system. The other problem is you sometimes get a kind of quite a hefty document and there's no summary. And what you find is that most people are busy. They just want to read a summary. What do they have to do? So the summary and the list of actions should be at the front of the report. It shouldn't be buried, which used to happen quite a lot. In some mid-report, it'd be a comment that a particular HUD isn't working. They should be all in a summary and a list of actions right at the start of the report. And the other problem, which often happens, is the employer files away the text system just in case as kind of as something to bring out if there's an inspection. I've got to have it done. I've had it done, and then file it. And that's not the right way, really. You need to take action to see what needs to be carried out in order to bring your system back up to scratch. So that brings us through from looking at the LEV design right through the procurement process and finishing with the thorough examination and test. Some further information here that's worth looking at and free to download is you've got the guidance documents I mentioned, HSG 258, the INDG 408 and 409. I mentioned one of them earlier. The other one is really just a pocket guide for the employee. The HSE, the websites, have a look at the websites, lots of information on websites there. There's also in the Institute of Local Exhaust Ventilation Engineers, and this is aimed at the LEV industry, and it's an individual membership. And the idea here is that you can, the people that join the institute become competent, and as they become competent, they can demonstrate their competency and they get competency cards. And so it allows them to build experience and competence in a number of different fields. They've also developed an LLB competency matrix to give people an idea of what qualifications you need, what guidance needs to be read, understood, and how long it takes to get that experience as well. So it's worth having a look at the LEV. Another one is that's an individual membership, LEV. IMARDA's the other one, Extraction Manufacturers and Designers Association. It's a newer organisation that's just really getting off the ground. This is manufacturers, so it's not an individual membership, it's manufacturers that come together. And the idea here is that employees tend to go to larger manufacturers, so it's making sure that they have the consistent message about the right type of LEV across the industry, so supply that information to end users. So there's some good information there. Thank you for listening, and if you've got further questions, please visit the HSE NI website. Thank you.